Good morning, everyone. Can you guys hear me okay?
Morning. Yep. We
Yeah.
can.
It's loud enough?
Yep.
Okay, so last day, well, it looks like there's still a few people that need to log in, so maybe we'll give them a minute or two. Um, how are you guys making out with the problems? Have you been working on the homework problems? So everyone knows that we have the midterm coming up. The term test one is coming up the week after next, right?
Yes.
And that test will have two questions on it. It'll have a combined loading question using the theories of failure, maximum shear stress theory and von Mises criteria, or the DE von Mises. And it'll have a question similar to the example that we're going to do today. Okay. So there'll be two questions on it. Now, last day, let's get going here. There's a oh, people are still coming in. So how are your other courses going, guys, while we're waiting? You have other midterms coming up this week, or you did some midterms?
No, we haven't done any midterms. I mean, we got process planning coming up soon, and thermodynamics the same week as yours.
Yeah, I talked to Mrs. Clayton. I think your thermal's on the Monday, right?
Yeah, that sounds correct.
Yeah. Okay. Well, that's good. There's space in between then. That's good. Okay, so let's get going. Last day, what we did was we went through lecture 3 of the fatigue stuff. And we talked about in the fatigue lectures, we talked about the Marin or Marin factors. And we discussed a little bit about, we talked about like the surface factor effect and how to find the theoretical endurance limit. And we talked about stress concentration factors and how to convert a static stress concentration factor into a fatigue stress concentration factor using the Notch sensitivity factor. So what we're going to do today is we're going to work through an example, okay? Now, this example will be posted if it's not already open on Canvas for you guys. Maybe if somebody can log into their Canvas under class examples. This is called shaft fatigue class example 2 solution. Um, if not, I'll open it directly after the class. So what you want to do is you want to make sure you get your textbook out, okay? And we're going to go through this quite slowly so that so everybody understands where to find all the information. So I'm going to open up my 11th edition. The references that are in the posted solution, I think, are either from the 9th or the 10th edition. So those of you that might have an older edition, it might be apropos for you. For the people with the 11th edition, as we work our way through the question, we will be adjusting some of the references and make sure that you see where these equations and such are coming from. Okay, everybody with me? Is everyone can everybody get their book? Okay, so if you have the 11th edition and you turn to page 359. Okay, and if I can find my, oh, and if you have the 10th edition, let's just see page it's on. If you have the 10th edition, it would be on page 338. Okay, so you'll see in the 10th edition, it's section 6-17. In the 11th edition, it's 6-19. And this is, it should see something called roadmaps and important design equations for the stress life method. So this is what we're going to use for a shaft design. Okay, so I got both of my books open here. So
I'm sorry, what page was it on?
which edition are you using?
11th.
It starts on page 359. You see it, section 6-19. Do you see that okay?
Yep, I found it.
Okay, so when we have, and this is similar to what you're going to see on your test. I just got to move some stuff over here. Okay, so here we have, excuse me, here we have a shaft, right? Has some loads on it. Now, keep in mind that these loads are always going to be acting downward as the shaft rotates, okay? These little boxes with the X's in them represent bearings where the shaft would be supported. So the shaft is supported at the center line of the bearing at A and the center line of the bearing at point G. And there would be a shoulder in here, right? So that the bearing can seat up against this machined surface here and this machined surface here. For this particular example, I haven't included that. Um, and that would be dependent upon the radius of that would be of that fillet that would have to go in this shoulder would be dependent upon the bearing that's selected. So next semester, and you'll see this when you do your gear pump design with Sebastian Ermi this semester. You'll see that when you do your SolidWorks model, when you pick a bearing out of the toolbox, you guys have used the toolbox in SolidWorks, right? Anybody? Okay, so Joe, so in the toolbox, you know, there's fasteners and all kinds of stuff, right? Okay, so what you're going to find when you design your shaft and you pick a bearing, and if you want to then mate the bearing to the shoulder, so that you don't have interference, you're going to have to make sure that the radius on the shaft is such that it has to be smaller than the radius on the inner ring of the bearing. Otherwise, you're going to get interference, or it's not going to go properly up against the shoulder. So what we want to do here is we want to find out based upon bending alone. Notice that in this particular case, the shaft doesn't have. We're not saying that we're putting so much horsepower through it. We don't know how to calculate the torque for it. So at this point here, all we're doing is we're trying to determine if the shaft is going to be safe against reversed bending. Okay. So the design equations that you have that we talked about in the lecture, I think you're going to be using the Soderberg criteria for Sebastian's course. You'll have a torque component. Okay. And they just go into the formula and you stick it in there, and he'll be giving you the stress concentration factors, which we'll talk about today, where he got them from. So um, to start out with this analysis, first of all, you see that it's the material is fairly soft. Okay, it's and if you go to table TA20 in your textbook, you'll be able to find the SYT and the SUT. In other words, the yield strength and the UTS for the material that the shaft is made out of. So to be able to do the analysis here, what we have to do is we have to determine what is going to be the critical point. So in other words, we're going to try and predict where the shaft would fail due to fatigue. So wherever you have your lowest fatigue factor of safety, and especially if it's less than 1, then we know that that's where it's going to fail due to fatigue. if all of the factors of safety turn out to be greater than one, that means the shaft will have infinite life, right? So before we can do that, we have to draw our shear and bending moment diagram. So we got to do a little bit of equilibrium. So let me just move on. Does anybody have any questions about the drawing here? Right, all the radii here I've made the same, 2 millimeters. Okay, obviously in an actual design you're going to have different radii. Okay, so just for this example, I've made everything the same. Okay, so turn to table TA20 in your textbook, right? Now this will be on a different page. So in the 11th edition, it's like 1000 something or other.
It's 1048
1048. Thanks, Mazen.
for the PDF. Yeah,
Yeah. Oh, okay. And that's that you're using the PDF. Okay, so
it's the same in the textbook as well. 1048.
no, I got it in the 11th edition. I got it as 1056.
I was talking about the 10th. Sorry.
Oh, you're with the 10th. Okay, so it's
Yep.
going to be different. Okay, so that's a key thing when you're writing your test, right? At the on the cover page of your test or right at the very beginning of your test, make sure that you tell me whether you're using the 10th edition or the 11th edition, okay? Because you're going to see that there's some variations in the equations, right? Now, we already talked about the Ka thing, right? But there's also the discrepancy in the pages. So if you don't tell me where you got it, right? Let's say that in this particular case, it's hot rolled. And let's say that you wrote down the UTS as being 330 and the yield strength being 280, right? Which is really the cold drawn, right? The CD, the cold drawn material properties. And if you don't tell me where you went to get those numbers, I can't give you part marks because I don't know where you got it from, right? But if I know where you got it from, I can look at the table and say, oh, okay, you just made a simple mistake by looking at the incorrect row. Okay, so it's not that you looked at the wrong material, you just looked at, you used the cold drawn number instead of the hot rolled number. Everybody understand that? Okay, so this is why the referencing is important. All right.
So we'll just write that at the top of our test.
Yeah, let me know which book you're using.
Okay.
Okay, and then you make a column down the right hand side of the pages that you write on, and put your references over here. Okay.
No worries. Thank you.
So if you put them over here, they're easier to see than if you integrate them into your solution. Okay. All right. It's also easier for you when you're doing the question um, to be able to go back and see where you're getting things, because you'll see later on I start to put information into the right hand column. It just makes it easier to find. Okay. Also at work, it's a good thing because what it does is if somebody asks you, like, 6 months or a year after you did some calculations, they'll say, well, where'd you get that number from? And you go, oh geez, I don't know, I don't remember, I did this like a year and a half ago. But if you put your references there, you know right away, oh, this is where I got it from. Okay, so once you find your reactions at the center line of the bearings, that allows you to go ahead and draw the shear and bending moment diagram. So I kind of cheated here. I used MD solids, right? And I went ahead and I calculated I put in the thing for MD solids, and I found the shear diagram and the bending moment diagram. Now notice something here, that at this particular point here, which is point C, okay, that is, if you look at the drawing, point C is this point right here, okay? There is no geometric change in the shaft here, but this is where we have our maximum moment. Now be very careful, because some books or some YouTube guys or whatever, if you look at another reference, excuse me for a minute, I need to clear my throat. They'll say that the shaft will always fail where the maximum moment occurs. Okay, this is not true. Okay. Um, so from my shear and bending moment diagrams, what I did was I found where I had a geometric change on the shaft. So at B, I have a shoulder. At C, I don't have anything. Okay. At D, I have the keyway. At E, I don't have anything. And at F, I have a shoulder, right? So to enable me, so once you have your shear and bending moment diagrams calculated, and you've gone ahead and found at each one of the places where you have a geometric change or not, you know your bending moments, you can then go ahead and start to calculate the critical section. So let's look at section B. Okay, so section B is this shoulder right here. Okay, now notice what's happening here. This dimension is 40. Okay, so this end here is the same if you want to make a note on if you've printed this out. Okay, so we're going from 40 millimeters, and we're stepping up to uh, 60 millimeters. Okay, and we have a 2 millimeter fillet in here. Okay, so what we need to do is if you go to figure A15-9, so I want you to go to that page, which is in the back of your book. Okay, so everybody turn to that page. And I'm going to pull up the 10th edition here. Okay, so you see here, we have three choices. We have axial loading, we have torsion, and down at the bottom, we have bending. Okay, so our stresses are bending stresses, they're reverse bending stresses. 150. Okay, so our R over D ratio is along the x-axis, and our D over D ratio is one of these curves, right? So if I just minimize this, go back to the PDF of this, we see that the R over D ratio, so this is this is 2 millimeters divided by the 40, and then this is going to be the 60 divided by the 40, right, to give us 1.5. So then I have 0.5, right, for my R over D, and I have 1.5. So I come up here, and where it intersects, that allows me to then find the KT value. So make sure you understand that. So when I did it, when I came up here, I said that, okay, if this line here is 2, I'm not quite at 2.1, right? So that's how I came up with the value for my KT value. So everyone might get a little bit different value for I just said 2.1. You could say 2.05 or 2.15. Okay. Does everyone understand where I got this KTB from? Does everybody see that? Does everybody understand that? This is what we did for static stress concentration factors.
Explain that again, the KTV.
Okay, so you need your R over D, right? So we're just looking at this shoulder right here. Okay, we're looking at this shoulder. It's stepping from 40 to 60. So little d is 40, big D is 60. Okay, so the radius is 2 millimeters divided by, so 2 millimeters divided by 40 gives me my 0.5, right? And my 60 over 40 gives me my 1.5. Once I have that information, I go to the back of the book, right? And for bending, okay, I go from my R over D ratio, I go up until I hit the 1.5, which is about here, right? So when you come across here, I said that that was 2.1. Okay, does that make sense?
Yeah, so like you're just kind of taking a guess at what the number should be.
Yeah, I'm making an approximation, right? I mean, because this diagram is so small in your book. I mean, it's no, I can't say that it's like, you know, if this is 2, right? I'm about halfway, so I said 2.1. how am I going to say 2.052 or something? That's impossible, right? Okay. And this is where you're going to have variability in your solutions if you talk to each other, all right? Because somebody might say, "Oh no, I didn't get that. I got, something else." So that's one of the reasons why I've taken those diagrams and I've photo expanded them, right? So that I can get a better resolution on the estimation of these KT values. You don't necessarily have to do that. Now you can go online, and there are calculators online to do these, but be very careful where they're getting their references from, okay? I would suggest you be a little bit weary about using stuff that's online because it doesn't necessarily use the Peterson, which are the industry standard stress concentration factors. So then we need to have our notch sensitivity factor, right? So if you go to if you have the 11th edition, you go to figure, I think it's 6-26. And if you have the 10th edition, it's figure 6-20. All right. So if we go to that in the 10th edition, we got to boot back way back to this chapter 6. This is why I'm saying you want to put tabs in your book, because this gets a little bit onerous when you're trying to do this with a PDF. So in this particular book, we want figure 6-20. Oh, geez.
I think it's 303 in the PDF. So you got a bit of scrolling.
Yeah, almost there. This is why I hate the PDF. Here it
So
is.
you can type the number in the PDF.
Yeah, I know that. Okay, so if I make this bigger, or if I go to 150, right? Okay, so what was our UTS that we found? The UTS value that we found was how much? Was it 100 KSI? From table TA20 for AISI 1006 for a hot rolled. The tensile strength, they're saying here that it's 43 KSI, but we're in the metric system, so it's 300, right? MPa. So you'll notice that on this figure that they give it to us in gigapascals, okay? So 300 megapascals is actually 0.3, okay, giga. And you'll see that on this diagram, we don't have a 0.3, all right? So again, we have to use a little bit of judgment here. Our notch radius is 2 millimeters because that's our fillet radius. So what I did was I said, okay, if this is 0.7 and 0.4, that's a difference of 0.3 in between there. So there's not going to be much difference between 0.4 and 0.3. So it's going to be very close. So I just came over here and I said, I'm going to use this point here where it intersects this dotted line. Okay. Not that I'm saying that it's aluminum. I'm just going to say I estimate that the 0.3 curve is that much below the 0.4 curve and come across, and I get approximately my Q value of 0.7. So again, this is where some people are going to get some variability in their solutions because they're going to get little bit different Q values. Now, I mean, if you say the Q value is 0.8, you're wrong. If you say the Q value is 0.6, you're wrong, right? Okay, if you say it's 0.9, you're wrong, right? It has to be somewhere in this range around 0.7, okay? Okay. Sorry, Alex, what do you want me to go through again? The value of Q. Okay, so your notch radius, okay, is 2 millimeters because that's the radius of the fillet, okay? So I have to come down this line here for the 2, right? And I have to hit the 0.3 gigapascals, but I don't have a 0.3 gigapascals. So basically what I'm doing is I'm approximating that I'm going to have a curve for 0.3 that goes underneath the 0.4 curve. Do you see that? Okay. So then where I find that that intersects, I'm going to assume it's right here. Do you see the cursor on the page? Okay. And then I go horizontally across. And I'm going to say that I'm going to approximate. Now, you could say that it's 0.68. You could say that it's 0.67. I'm going to say that it's 0.7 for my Q value. Okay. Any other questions about that? Are we good with that? Okay. So if we go back now to this solution, you'll see that now I have my static stress concentration factor. I have my notch sensitivity factor. Okay. Now I can calculate my fatigue stress concentration factor because in the older textbook, it's equation 7-31, 1 plus Q times KT minus 1. Put those numbers in. I find the fatigue stress concentration factor. Okay. Now, at this point here, what I'm doing is I'm finding the maximum stress. Okay. I'm taking, remember, this MC over I is the nominal stress. Okay. And to find the maximum stress at that point, I have to multiply it by my fatigue stress concentration factor. So I take my MC over I, right, for the smaller diameter. Okay, it's based on the 40 millimeters, so it's based on the smaller diameter. Okay, multiply it by my stress concentration factor. So I get a maximum stress at B of, let's say, 32 MPa. Okay, so this is what we're going to come. So maybe I should have put here sigma B max and sigma B max. Okay, so you can change that when you print this thing out or whatever you want to do, or upload it from your Canvas page. So now what I do is I just move to my next section. Okay, so the next one where I have it, well, let's take a look at where we have the maximum moment. Right, when we did our shear and bending moment diagram, we saw that at this point here, C, we had our maximum bending moment. Now, is there a geometric change in the shaft at that point? Is there a keyway? Is there a fillet? Is there a snap ring groove?
No, there's no geometric changes.
There's no geometric changes, right? So if there's no geometric changes, there's no KT, there's no static stress concentration factor, which means that the nominal stress is equal to the maximum stress. Okay, so if there's no KT, there's no Q, we can't find a KF, right? Which just means that your KF and your KT are going to be 1. Okay, so your nominal stress will be equal to your maximum stress. But we should investigate it, okay? So that's what I've said here. At this point here, there's no KF, okay? And so I see that I get 12.06 megapascals for my stress at C. Now, at section D, all right, we have a keyway, all right? Now, because we don't know the radius on the keyway, and we'll learn this next semester, a more detailed analysis of keyways, I used this value here from another reference, okay? So this D represents a book by the name of Deutschmann, okay, which directly gave me for that particular type of keyway, and if you look at it, it's a sled runner keyway because it's curved at the ends, okay? If it was a profile keyway, this would be squared off corners, all right? So I found this directly. Now, if you look in chapter 7 of your textbook, this table here, 7-1, and it's the same table in both editions. You'll see that they give us, and this is also in your notes. They give us this table 7-1. Okay. Oh shoot. Okay. So you see here, they're telling us that these are first iteration estimates for stress concentration factors, okay? Now, notice what they show here, that it's KT and KTS. So this is not the fatigue stress concentration factor. This is the static stress concentration factor. So to be able to convert, so they tell us for bending, it's 1.7 for the KT value, okay? To be able to calculate the KF, we would need to know what the radius at the bottom of the keyway is. Does everyone understand what I mean? Because we need to find Q. Okay. So this is not the KF, this is the KT. So you need the Q value to convert this to a KF. Any questions about that? Do you understand this? Or do I need to explain it more?
So just to make sure I understand this right, you take that 1.7 and you need the Q value
Yeah.
because it's a KT, not a KF.
Yeah, but we don't know now when you cut a keyway into a shaft, you use standard keyway cutters, okay? And those keyway cutters, whether it be used on a horizontal mill or a vertical milling machine, have ASME standard radii on them, okay? So I'm just going to turn the camera on here for a minute. Can everyone see that okay? Right, so
That's good.
if you look at, let's say we have a shaft like this, right? And we put a sled runner keyway would look like this because it's cut with a horizontal milling machine with a round cutter like this, okay? The profile, or what some people call end mill keyways, if we looked at the drawing, would look like this from the side, right? Or if we do a broken out section, if we do a broken out section here, okay? From the top, they both look the same. So from the top, this looks like this. And from the top, this looks like this. They look the same from the top view. This one's cut with an end mill or what some people will call a center cutting end mill. Okay, so it can plunge directly in and then move along and then come back out here. Okay, to cut the keyway into the shaft. Now, from the side, right, if we were to take a section view, oh, excuse me. The keyway is going to look like that. Okay, so this is a section view through the keyway. So these cutters, whether it be a horizontal mill or a slot drill or center cutting end mill like this, will have and leave a certain radius right there at the root of the keyway. All right. So this is the area where you get your stress riser. Okay, just like we saw in the video, right, and in the notes. So if we don't know this, right, we can't go to figure 6-20 or figure 6-26 like we did before. We can't find the Q value, right? And we know that Kf is equal to 1 plus Q times Kt minus 1. What table 7-1 is giving us is this. Okay, so unless we know this R value, so let's say that I gave you a test question and I asked you to analyze the position where the keyway is, I would have to tell you to use first iteration methods, but I would have to tell you what the radius at the root of the keyway is, or show you a drawing like this of a section view so that you could find the Q value. And then from the Q value, you'd be able to calculate what the Kf would be. So in some textbooks and in some references, they will give you this value here directly. Okay, and that's what I got from this what I use a double D like this for the Deutschmann textbook. He directly gives you the Kf values. And again, they're approximations, right? And we'll learn next semester in sixth semester. We'll go through like an FEA analysis, finite element analysis for keyways about how to find these to be more accurate on the KT values and more accurate on the standard R values to find the actual KF values. Okay, does that make sense to everybody? So for now, okay, I'm just going to use, for this particular example, I'm going to use the value that I got from the other reference. Okay, any questions about where this is coming from? Yes, no?
I think I understand it.
That's pretty clear.
Okay, all right. So I'll turn this off. So these are just estimates, okay? So these are what they call first iterations. So if you're just doing an initial design, okay, you can use these estimates. And then because you know that you're going to have to do another iteration probably with your design, which is what you're going to do with your gear pump, because you're going to do the another full analysis in sixth semester on it. So in this semester, you're going to use some estimated values and the Soderberg criteria, I think, to find your sizes and stuff and do, because the key thing for this semester is to get the drawing done, okay, and the assembly. Then next semester, what you're going to do is the actual uh, heavy duty thorough analysis of the shafts and the gears and the bearings and all that stuff. Okay, so that's where that's heading. So that being said, if we come back to this example again, I see that after I calculate my MC over I for the keyway, I multiply by the stress concentration factor, fatigue stress concentration factor that I got from the other reference, and I see that the maximum stress at D is going to be 18.4 megapascals. Now, at E, if you go back to the diagram, again, there's no stress concentration factor here, right? And actually, the moment at E, when you look at it, right, is this 194. it's actually less than what we had over here. Here we had 250, let's say 256. So obviously, if we got a fairly small stress here, we're going to get a smaller stress here. That's why I'm not analyzing it, right? Now, at section F, my KF is going to be the same because I'm stepping again from 60 to 40 and my radius is the same. Now, if the radius was different, I would have to again find my R over D and my D over D, find my KT, and I'd have to re-find my Q value and recalculate the KF, okay? But because they're the same and the bending moments are less at F, I know that the stress is going to be less at F, okay? So then what we do is we look at each one of these sections, okay? We say, okay, at B I had 32, right? At C I had 12, at D I had 18, right? So which one's the worst case? Well, we predict failure to occur right here, okay, at this shoulder, okay? Now, be careful because if you were to look at this shaft, right, initially, without doing any sort of analysis or anything like that, would you predict that it would fail at this shoulder? Anybody? Where would you expect it to fail? Like what would be your first your instinct to say where this shaft would fail due to fatigue, where you would start to see a crack propagating? What do you think?
Well, I think some people would say the keyway.
Yeah, a lot of people would. I think a lot of people would say the keyway, right? Okay, because it's got a really sharp corner, right? When you cut it, okay, and it's in the middle of the shaft, so everyone would think, oh, okay. So even though when we look at, oh, I'm gonna rotate this. When we rotate this, it's got a fairly high moment, right, where the keyway is, right? So the expectation I think a lot of people would have is that we would have failure where the keyway is. But in this particular case, it's over here where the shoulder is, and it's not where we have the highest moment, okay? Right? The highest moment that we had was at point C, right here, where we didn't have a stress concentration, okay? So this is where we got the failure predicted. So this is why I'm saying you got to be a little bit careful. Assume anything. You do the analysis for each geometric change on the shaft, and then from that, you can determine where you're predicting failure. Now remember, we are only comparing maximum bending stresses. We haven't included a torque here, okay? So at this point here, you want to go to your textbook and you'll see that there's a difference in what I've written here and what you have for finding your theoretical endurance limit, right? Yours, what does yours say? You don't have 0.504 here, right? What do you have?
I got 0.5.
0.5, okay. So in the 8th edition and I think in the 9th edition also, for some reason they used 0.504. And then in the 10th edition and the 11th edition, they dropped the 04, okay? So here, if you guys were to do this with your numbers, this would be 150 MPa, okay? So there's going to be a little bit difference when you're using the 10th and the 11th edition versus where I got these values from. I'm just going to put this in here so we can see the difference as we're working through. Okay. So there's 1.2 megapascals difference between the two. Now, you're also going to see a difference here, depending if you're using the 10th edition or the 11th edition, right? So I want you to go through, if you're using the 11th edition, what would you get for your Ka value here? Okay, so somebody that has the 11th edition, calculate what you get for Ka.
Do you know what page it's on?
Do you have the book?
Yeah, I had the 11th edition.
Okay, so the 11th edition, if you follow that roadmap, it will tell you. Right? This is why I'm telling you guys to put tabs in your books, okay? Because what you don't want to be doing during the test is flipping, trying to find stuff, right? You don't want to waste time doing that. So this value here of 4.51 and this exponent will be different in the 11th edition. So when you plug your values in using the 11th edition, what do you get? Okay, to 4 decimal places, Ravi. What do you get to 4 decimal places? 8817. Okay, so you see that there's a difference between the older edition and the newer edition here. Okay, so again, this is why it's important you tell me which edition you're using for your test. Okay, does everyone see how to get 0.8817? Be careful, you put in 300, not 300 times 10 to the 6th. Okay, for the KB value, which is the size factor, it's the same in the 10th and the 11th edition, but notice here that we use the smaller diameter always, okay? Right, because that's where the failure will occur, on the smaller diameter. So you should get the same value here in the 11th edition of 0.8356. Now, we don't have any, the type of loading that we have is reverse bending, right? We don't have reverse torsion or reverse axial, right? So the reverse bending, Kc is equal to 1. It doesn't tell us anything about temperature, so we assume that's 1, right? Our stress concentration factor here we got from before, right? So I invert that to get my Ke value, what they call the miscellaneous factor. It also doesn't tell us anything in the question to assume greater than 50% reliability, so this becomes 1. And now what I can do is I can calculate, and this would be my fully modified endurance limit. Why is it fully modified? Because it includes the stress concentration factor. So if you, for those of you with the 11th edition, instead of using the 9948, if you use the 8817, right, what do you get for your value here for your SE, your fully modified endurance limit? Okay, so instead of 71, what do you get for this value here? So here you're gonna put the, make this a little bit smaller. We had up here 8817. All right, so you'd put 8817 in there. Right, instead of the 9948. And then
You
what do you,
get 62.94.
okay? So there's a little bit of a difference, okay? So it'll affect your answer a little bit, okay? So just remember that this includes the stress concentration factor, okay? So what we're after is the factor of safety against fatigue. So if we use the Soderberg criteria, okay, and it wouldn't matter if we use the Goodman criteria or the Soderberg criteria, right? Because this mean stress is going to go to 0, right? So the factor of safety against fatigue is just going to be the ratio of SE over sigma A, okay? Now, I used up here, the stress concentration factor was included. So this is my uh, fully modified endurance limit. If I use the fully modified endurance limit here, I use the nominal stress here, okay? So in other words, I don't put the KF in both of these. I put it in one or the other. So if I left it out up here, then I would use the maximum stress for my sigma A, right? So here you can see I've calculated the nominal stress at point B for that shoulder, all right? And then I took the ratio of what I got, okay? So you guys got 62.94. So if we put, instead of the 71, if we put here 62.94, what would you get for your factor of safety? So 62.94 divided by 18.09. So make sure that both are in mega, okay? So that's 71 times 10 to the 6, right? And 18 times 10 to the 6. Don't mix your units, else you're going to get some weird number. What do you end up if you do the 62.94 divided by 18.09?
I got 3.479.
So 3.4,
479.
let's say 8.
7. Okay.
Close enough, right? So you see there's a difference depending upon which edition you're using, okay? So again, this is why it's important that you tell me which edition you're using, okay? So if we use the Goodman criteria, we get the same answer as I said before, because this mean stress would go to 0. Does everyone understand why the mean stress goes to 0?
No.
No?
Can you explain it, please?
Yep. Okay, let me flick on the camera here. Remember that what we have is we have a case of completely reversed bending, right? So what's happening to the shaft is this, right? Completely reversed, okay? So this would be our sigma A, and this is minus sigma A, minus sigma A, and this is your sigma M, all right? So when you use either one of these equations, whether it be the Soderberg or the Goodman, right? You always have your alternating component affiliated with your fatigue material property. Okay, in this case, it's the modified endurance limit or fully modified endurance limit. And then you have your mean stress divided by, now if you're using the Soderberg, this becomes SYT, and this will be 1 over NF, right? And if it's the Goodman criteria, plus, right? So you see here, that'll go to 0, and that'll go to 0. So both of these are the same, right? And then basically then you're just looking at sigma A is equal to over SE is equal to 1 over NF, or your NF is equal to the SE over the alternating component of your stress. That makes sense now?
What about the SYT and the SUT? Aren't those different values?
Yeah, but if this is okay, let me ask you this. If I have 0/10 or 0/50, what are these both equal?
They equal 0.
Right? Okay. Right? See what I'm saying? Now, what I was saying previously is you got to be careful, because if you put the KE equal 1/KF into here, then this becomes the nominal stress, right? The other way to do it is if this has no KE in it, which means you haven't included the stress concentration factor, then this here becomes sigma max, which is equal to KF times sigma nominal, right? So you can see that if you put it in both places, you're going to end up with SE/KF squared times sigma A. Okay, so you use it in one place or the other. Does that make sense, Alex? Okay, so just be careful, and this is why in your margins you want to make a little note to yourself, includes KF or doesn't include KF, so that you don't mix the two when you get to the final part to find your answer for your factor of safety against fatigue. All right. Is everybody okay with this? Does everyone understand why the sigma m goes to 0 and why we got to be careful about where we put our KF value, and we don't want to use it twice?
No. Can you repeat it again? I've been having internet problems, so I wasn't able.
Oh, yeah. Okay, Mike. So if you include this miscellaneous factor, which includes the stress concentration factor, and you use, so this would become what I call the fully modified endurance limit, okay? Then you use the nominal stress for your sigma A, okay?
Okay.
If you don't include the KE, which is 1/KF, so this is just the modified, not fully, so we can put a little note here, not fully modified, okay? In other words, it doesn't include the stress concentration factor. Then you use the maximum stress for your sigma A, not your nominal stress. You use it one or the other, okay? Is that okay, Mike? Oh, maybe we lost him. Does anyone else have any questions about this? While we're waiting for Mike to log back in, hopefully, does anyone else have any questions about this? Did everyone understand this? Does anyone have any questions about the procedure that we just went through? Stefan, do you have some questions you would like to ask?
honestly, I'm just going through the homework and the notes now, trying to wrap my brain around it. I don't know enough at the moment to ask questions. I'm just doing my best to follow along where I
Okay.
can.
Okay, so make sure that you read through the sections in the chapter, right? Before you start to try to tackle some of the problems, right? Are you okay with the Marin factor things, the Ka, Kb, and all that?
Getting getting there. It's gonna be rough. Last week was not a great one, so I'm a little behind on my studying. But
Okay. Did you guys have tests last week or something? The class, yes, the class examples will be posted, Mike. Okay, I think it's actually it's open. If you go into your Canvas right now, I think this example, I'll check. Let's see. I'm just going to log into Canvas here. Okay, so if you go into modules, just bear with me for a minute, guys. I'm just checking to make sure that this will come up for you guys. Okay, so if you go into Canvas, right, and you go to modules, my stuff isn't open because I didn't open these. Okay, so yeah, I did that. Yeah, and I read that. Why does it not? Anyways, I'll get out of the student view. If you go down to the bottom, you'll see class example solutions, okay? And you'll see this is the one that we're doing today. All right, so it's there for you, okay? All right. Everybody, is anybody in Canvas? Can they see that? So what
Yeah,
I've
we can
got,
see it now.
okay, good. All right. So what you've got on the screen is you've got, or from the in Canvas is you have this this solution here, right? With the older edition, you might want to update it or rewrite it with your 11th edition. Okay. Now, the other thing that we should, even though we use the Soderbergh criteria up here, which we know takes care of yielding for cycle yielding, and we use the Goodman criteria here, if we wanted to find the factor of safety against yielding, so you see the difference here is that your alternating component is based upon the SYT, all right? Now here I use the nominal stress, right? Some people would use at that point B, what did we get for B for the maximum stress? 32.01. Yeah, try this. Do instead of 18, put in here 32. Oh, nice if I use a 0. If you do that, what do you get for the factor of safety here? 170 divided by 32.01. Anybody? What's
I
one?
got 5.31.
Yeah, okay, so it's substantially different, right?
Yeah.
So you'll see that the reason why I use the nominal stress here is if you read in your book, it says that you're not supposed to apply the KF or the KT factor to a ductile material, only to a brittle material, all right? Now, there's two schools of thought here, and I think we talked about this before. We could have used, in here I use the KF, right, times the nominal stress. Some people will say, well, because you're looking at yielding, you should use the KT. And some people will say, no, you use just the nominal stress, okay? So when you're doing your test, all right, state what you're doing, okay? Say, I'm using the nominal stress, I'm not including the KF, or I'm using the KT, right? Because it's really a judgment call, and it depends on where you work, how they do it, and what the philosophy of the design people are that at your workplace, okay? Now, if your factor of safety came out to be less than 1, right? This means that we would not have infinite life. So at this point here, just due to pure bending, right, because our factor of safety against fatigue is greater than 1, we would say that the shaft would have infinite life. So that means that it's going to have at least 1,000,000 cycles. We don't know if it's going to be 10 to the 7th or 10 to the 8th or 10 to the 9th. All we know is it's going to be 10 to the 6th or better, all right? So if the question says, will the shaft have infinite life? We would say, yes, it has infinite life because the factor of safety against fatigue is greater than 1, okay? But if the factor of safety against fatigue came out to be less than 1, all right, that means that if you recall, back to the SN diagram, where this is the number of cycles, right? We had, and if this was 10 to the 3, we had the curve went like this, right? So this value here was our SE value, and this corresponds to 10 to the 6th cycles, right? So this is anything on this side here is infinite life predicted, okay? So your NF is greater than 1. Anything to this side over here is finite life, right? Okay, and this is where you'll get your NF less than 1. So in this region here, you had the equation SF is equal to AN to the exponent B, right? Okay, that was Basquin's equation. So what this allows us to do then, knowing the level of the stress, so this if this was the point, this would be SF, okay? So this is basically, this equation here is the equation of this line between 10 to the 3 and 10 to the 6th. If we know this, which we know because we did the analysis and we got an NF less than 1, right? We can then determine the number of cycles to failure, okay? So even though our factor of safety here came out greater than 1, I wanted to illustrate how you do this in the example that's posted. So let's assume that when we did find our factor of safety, that it was less than 1, okay? So what happens here in this equation, and this is equation, I think 716 in there in the 11th edition, is that this sigma A uses the nominal stress, and we include the KF in the SE when we calculate the values of A and B, right? Now, you'll see here that what I've done is I've assumed the little f value was 0.9, okay? And you can do that for now, all right, if you run into this situation. Next semester, we'll look up the actual the constant f using the little diagram that's in the textbook, okay? Because it will change. So for now, just use 0.9 for the little f. So if I do this, and it's because our value came out greater than 1, this is not really valid, but it illustrates how to use this, right? And the key thing here is that the sigma A is the nominal, and in the A and the B, this is the fully modified endurance limit. It includes KF, okay? So you get your A and your B value, and you'll see here, this makes no sense at all, right? Because it comes out greater than 10 to the 6th, okay? Right? So we really know it's not applicable, because if our stress was high enough that we got a factor of safety less than 1, this would come out to be something less than 10 to the 6th. Does everybody understand what I'm saying? So in reality, if our factor of safety was less than 1, our cycles would be less than 10 to the 6th when we put our numbers in here. Okay? Any questions about that?
Just so I understand this, when you went to the chart, you said that 10 to the 6th, it had to be less than 10 to the 6th is what your value should have been.
Well, what I'm saying here, Mike, is if we got a factor of safety less than 1, okay, which we didn't, okay, all right. If we got a factor of safety less than 1, right, then this equation now becomes valid, okay, and it allows us to then go ahead and calculate the number of cycles to failure, right? So it should end up to be somewhere between 10 to the 3 to 10 to the 6th, okay. So if we went back here, and we know that this 18.09 is too low to cause a factor of safety less than 1. But if let's just go up, let's try something here. Let's say that we had a stress that was larger or somewhere in between the yield strength and, no, let's say it's the yield strength, okay? So let's say that we got a stress of 180 MPa. That means that the shaft is going to fail, okay? If it's 150, it's under the yield strength, all right? So it's not going to yield, right? but we could get a factor of safety of less than 1. If we go down here and we look at how we calculated the factor of safety after we did all of this stuff, right? We took the ratio of, in your case, 62.94, right, over 18. So let's make instead of using 18 in here, right, do this calculation. Let's make this 80. Okay, so 62.94 divided by 80 megapascals. What does that give you? And let's just put it over here in the margin. So 62.94 divided.
0.78.
Okay, so 0.78. Okay, so what do we see? Right away, our factor of safety is less than 1. Okay, which means now we don't have infinite life. Okay, we know that we're going to have less than 10 to the 6 cycles. Okay, so what did I just say I'm going to use for this value here? What did we put in here again? Sorry, 150? No, we put in,
Yeah, are you
no,
talking
no,
about?
we put in 85 here, didn't we?
No, we put in 80.
80. Okay, so the 80 gave us 0.78. All right, so now we know the thing isn't going to last forever. We're not going to have infinite life. Okay, so this is the nominal stress. Okay, we know the fully modified endurance limit. So if we come down here and if we put 80 in here instead of the 18, okay? Okay, so let's put 80 in there. Okay, so if I put 80 in there and let's do the calculation.
Negative 0.403.
Doesn't sound right.
Wait, so I did 80 over 1026.6. Is that all you wanted me to do, or multiply it by?
The whole thing.
I got 537,858.97.
Okay, so in engineering notation,
That is.
right?
Oh,
In-
sorry.
I got, let's say 538 times 10 to the 3.
Yeah, that sounds about right. 538.
I'm going to write it like that, right? Okay.
Okay.
So you see what happened was when we had a factor of safety less than 1, we were able to calculate the number of cycles to failure. So this thing's only going to last 538,000 cycles instead of over 1 million. Follow me?
Yeah.
Okay. So it's not going to have infinite life, right? And this equation, this SF equals AN to the B, only works if you get a factor of safety less than 1. Okay. So if that means that if I had this many cycles, then we can change this, right? We can figure out, let's say that this shaft was running on an electric motor that was running at 750 RPM, 1750 RPM, right? If you put in here the 538 times 10 to the exponent 3, right? And figured out here, you can figure out how many minutes it's going to last, how many hours it's going to last, how many days it's going to last, how many years it's going to last. Okay. So this is how people figure out warranties. They work backwards from this. Okay. So they say, oh, I want a 3-year warranty. I know that typically this thing's going to run at a certain RPM, right? They figure out the number of cycles, and then they solve for what the stress should be, and then they go back up here, up to the top, and they figure out, okay, what should be the size of this component so that I only get that. So I get that stress level, and it's only going to last 3 years. So you work backwards, right? So if I do the 538 and divide it by the 1750, right, I get 307.4 minutes, right? Not very long, right? Divide that by 60, I get like 5.123 hours, right? Now, are you going to design something that's only going to last 5 hours? Now, that depends, right? If it's intermittent use, like a toaster, right? And you're only going to put a 30-day or a 60-day warranty on it, you'll say, okay, maybe if somebody uses a toaster on an average of once or twice a week, right? And the toaster, to toast the toast, it takes like 2 minutes, right? Or 1 minute or whatever it is. They said that, well, that thing should last at least 30 days or 60 days. You see where I'm going with this? You understand?
Starting to.
But this is only valid when your factor of safety of fatigue is less than 1. Okay? So I won't be asking you to do these number of cycles on the test. Okay? I'm basically going to ask you, I'm going to give you a shaft, and then you're going to have to do the shear and bending moment diagram, look up the properties, find the Marin factors, find the factor of safety. Now, the other thing too is because, I mean, it's a test, right? And you have limited time. So if I gave you a question like this, it might say to you, find the factor of safety at point F, or find the factor of safety at point B, or find the factor of safety at point D. Okay? Because you don't have time. We just spent what, an hour and a half, right? Analyzing this section, this section, this section, this section, this section, right? It takes a long time to do the full analysis. But this is what you would have to do in the workplace. You'd have to do the full analysis. All right. So on a test, I'll say at point such and such, right? What is the factor of safety against fatigue? And is it going to have, and will the shaft have infinite life according to that point? Okay. You guys want to take a break for a minute? 10 minutes?
Sounds good.
Okay. I'll see you back here. It's about 10:30. I'll see you in 10 minutes. Okay. Okay, is everybody back?
Yeah, I'm back.
Yeah, I'm back as well.
Okay, so does anyone have any questions about what we've done so far today?
So this example is just pretty much in depth, and the test question, like you said, you'd ask us, um, like only up to a certain point, A, B, F, or G.
Yeah, exactly. So if you look on Canvas, under the modules, I'll just pull it up here. I'll close this. No, I don't want to save that stuff. Close this. And you go to, these are the problems for fatigue, right? You see that there's this one here is just practicing the values for Ka and finding the KTs and stuff like that, right?
It looks similar to question 2, but without the thing at E.
Yeah. Yeah, so if you look at these two equations, if you look at this question here, right? So right, this equation says, I hate this viewer thing. The shaft shown is machined from 1040, right? It rotates at a certain RPM and is supported by the bearings at this position here and this position here, right? And you know that these two applied forces are 2,500 and 1,000. Determine a minimum fatigue factor safety based on achieving infinite life. So in this particular case, you would have to look at point C, point D, point E, where there's a keyway, and point F, all right? So on the test, it may just say, determine the factor of safety against fatigue for point D,
Okay.
okay?
All right, that's what I was asking. Thank you.
And so if you look back here, if we go back into here, you'll see that this is now open for you guys. That's the problems. These are the solutions. So you'll see this one here, it just gets into the idea of finding the KAs and KBs. And because it's non-rotating, you have to use the DE, right? And then here you can see we have the shaft, right? We draw the shear and bedding moment diagram after you find your reactions, right? You look up your material properties, and then you start to look at your, now, does everyone understand where, did I explain to you guys where this equation here came from, the 32m over pi d cubed?
Not that I can remember.
Okay,
I don't remember.
so if you remember for what we did in strength and materials, and this is talked a little bit about in the textbook when they do the theories of failure and the design equations for shafts. If you remember, we had for bending stress and for torsional shear stress, we had TR over J, right? Remember that? I hope,
Yes.
right? Okay.
Yeah,
So we know that the maximum bending stress occurs at the outer surface. So for C, we would always use d by 2, right? Which is equal to the radius. And obviously the radius here is d by 2, right? And then for a circular cross section, remember that you had I was equal to pi by 64 d to the fourth, and j was 2 times that. So j is pi by 32 d to the fourth, right? So now what I'm going to do is I'm going to substitute this into this and this into this, okay? So over here, this is going to be m times d by 2 over pi by 64 d to the fourth. Okay, so the denominator of the denominator comes up to the numerator, and this denominator goes into the denominator. So that ends up with a 32, right? The m stays, the pi stays in the denominator, and then you have d cubed because you have a d in the numerator and you d to the fourth here. So this is just a short way of calculating the bending stress, okay? We can do the similar thing for shear stresses, where this is, we have t, and then we put in d by 2 here, and then our j is pi by 32 d to the fourth, right? So same sort of stuff happens. The denominator of the denominator, right, goes up to the numerator. This comes down into the denominator. So that leaves you with a 16, right? 32 divided by 2 times the torque over the d is in the numerator, and d to the fourth is down here, and you get d cubed. Okay. So if you see these 32m over pi d cubed and the 16t over pi d cubed, it's basically just recognizing the fact that the maximum bending stress occurs at d by 2 for a circular cross section, and that the maximum shear stress for a circular cross section also occurs at d by 2. Make sense?
Yeah, it made more sense. Thank you.
Okay. So these are what people in design use. Okay, they don't go back to the fundamental ones up here, right? And that's what you'll see in some of the design equations that you'll be using and that are shown in the notes for this particular course. So that's where this comes from. So in this particular case, what I did was I looked at, because at E, right, section E, we don't have any stress concentration here, right? So that means that it means that the nominal and the maximum are the same. So we have 55.62, right? And then at the shoulder, we know the radius is 3 millimeters and the little d. So we do our R over D and D over D to find our KT value. And then we go to figure 6-26, and these are all to the 11th edition. The Q value is I got 0.81, so I can calculate my KF, which then I can calculate my maximum stress at point D, okay? And then for here, oh, what happened? I'll have to rescan this. Page 4. It skipped, I guess make a note. Rescan solutions. Let me pull up my PDF file here. I guess it's stuck together in my scanner. Oh, I'm glad we looked at that. Gotta love technology, eh? Okay. Class examples. Give me 1 minute. Now, hopefully you can see this because it's written in pencil. Can you guys see that okay?
Yeah, looks
Okay.
good.
So you see what I've done here is I've gone through for my section E, which has no stress concentration factor. I get my maximum stress to be, let's say, 56 MPa. And then where I have my shoulder, it comes out to around 100, 99.8. And then here, I have my section where I find my my shoulder. I got to find my R over D, D over D, and then I find my stress here. So what I find out is the shoulder at D is actually the critical point. So that means that this shoulder at D here is the critical point. Okay. And then once I find that it's the critical point, I go ahead and I start doing my Marin factors. Okay. So I find my theoretical endurance limit, right? Multiply by, take my SUT here and multiply by 0.5, right? And then I start doing my KA, so it's a machine surface. My KB, use the smaller diameter. It's reverse bending, so this is one. It doesn't say anything about temperature, so this is one. Now, here you see that I made a little note to myself that I included it over here in my maximum. So I've already multiplied this by the 1.57. That's just to remind me when I go to find my factor of safety that I'm already using the stress concentration factor in my value of my stress. So I didn't include it in my SE. So this is, in this case, I made the choice to not put it in the SE, but I put it in the stress, okay? And then I come up with a factor of safety, which is greater than 1. It just means that it has infinite life, okay? That is, it's greater than 10 to the 10 to the 6 cycles. So if you get a question on the test and it says, will the shaft have infinite life according to this point, right? As long as this comes out greater than 1, then you say, yes, it has infinite life, greater than 10 to the 6 cycles. If it's less than 1, you say, no, it has finite life, less than 10 to the 6 cycles. Make sense? But the procedure is the same over and over and over again. The methodology is the same. Okay, so if you follow that roadmap, right, you should be good. Questions? Stefan, is this kind of sinking in a little bit now? You've seen it?
Yeah, it is. Like I took a screenshot of this too, just so I can go back over it later.
Yeah,
Yeah,
that's cool. I'm gonna rescan this and I'll put it. It's already
no,
open, but I
that's
guess page 4 and 5 stuck together.
that's even better.
Yeah, so
Yeah, just
I'm gonna rescan it and I'll post it with the page 5 included.
yeah, sir. You're very good. It's my own fault that I'm behind, so don't worry about that. I'm
No,
gonna.
no, I just want everybody to do well. I know you guys are busy and I know this is a challenging thing, this online stuff. So, you know, I'm trying to be understanding. But yeah, you gotta like over the break, make sure you guys spend some time on this, all right? And you know what you're gonna be responsible for. I think I'm being pretty forward about what kind of questions you're gonna get and what to expect. So just please be prepared, okay? All right, because next, yeah, Mike?
I was gonna ask for the sections E, there's no stress concentration. Is it because on the diagram it reaches to the max, right?
At
Manufacturing.
section E,
Yeah.
if you look at, can you see this? Section E, right? Okay,
Okay.
okay. There
Yeah.
would be no stress concentration. In other words, even though I put a keyway here, okay, we haven't been
Yeah.
given any information about it. So if I gave you a keyway, I would give you the KF value for the keyway.
Okay.
All right. All right. So next semester, when we do more analysis about keys and the stress concentration factors for keys, then you'll get a more in-depth analysis for it. Okay,
Okay,
sound good?
sounds good. Thank
So,
you.
but if I do give you a key, I will tell you either the KT value or the KF value. If I tell you the KT value, okay, if it says the static stress concentration factor for the key is 2.1, I have to tell you what the radius at the bottom of the keyway is, or I have to give you a diagram that shows you the radius, because you got to find because you need the Q value, right? You got to find this notch sensitivity value. If you don't know the radius at the bottom of the key, you can't find little q, and you can't convert the KT to a KF,
Okay.
right? So you'll be given all the information. Now, if you go on Canvas, you'll also see that I closed my Canvas here. But if you go on Canvas, you'll also see, you should see, does somebody have Canvas open? Anybody?
Yeah, got it open.
Okay, so Stefan, if you look on the home page over to the left, you should see what? Modules, home, modules, assignments. No, do you see assignments?
No.
No, there's home modules,
Great.
grades, announcements, and chat.
Okay, so see the chat, all right? So during the test, I will be in the chat. Okay. So I will have the chat open for you guys. So if you have a question while you're doing the test, right, during the test time, I will be there to answer your questions. All right.
All right.
I don't know what other professors are doing for their tests. I don't know. Are they doing that, or what are they doing for you guys?
Most of them are just opening a PDF and then sitting in a Zoom meeting for 2 hours. And if we have questions, we ask them.
Oh, so they're doing a Zoom meeting?
Yeah, that's how I did it in the summer. I haven't
Oh,
done a midterm this semester so far.
oh, okay.
Yeah, I
So
didn't really understand why they had us in the meeting, but
yeah, to me it just uses bandwidth, right? I mean, I would. Are you guys okay with? I mean, a lot of people, like when we have these Zoom lectures, are using the chat thing in Zoom anyway. So I just figured that people are comfortable using, like, typing in a question, right? You know, is that okay?
Yeah, that's fine.
Everybody feel comfortable with that? I mean,
honestly,
that
prefer
way,
not.
that if we're in the chat, right? Like if we go to Canvas and we go into the chat, then there's none of this private stuff, right? It's basically everybody can see your question. So if you have a question, like maybe somebody else has the same question, you know what I mean? And then I can answer it, and everybody sees, oh, okay, that's what that's supposed to be. You know what I mean? So
Yeah,
we just
and honestly, just having it in text format, at least to me, is preferable. There were a couple times during the test where where it was a Zoom meeting where, like, when you're focused and then suddenly a voice just comes out of nowhere and you jump 3 feet in the air.
yeah, or it also interrupts your train of thought. I thought that's what I
Yeah.
thought.
So
You know what I
at
mean?
least at least for me, that's preferable.
Yeah. So I don't know if in Canvas in the chat thing, if there's a little ding thing that comes up or not when somebody puts in a thing. I don't think so. I think it's silent. So, but anyways, at least that, I think that like typically, um, if I'm running a test like face to face, so I got what there's going to be like almost 100 guys people writing the test at the same time. I'm running around the classroom like a madman, and a lot of the times it's the same question over and over and over and over again, right? So this way, if it's right in the chat, right? I mean, just keep your chat open, and chances are that maybe somebody has already asked that question. You know, I mean, I don't have a problem with that, and I don't think. I mean, you guys are in fifth semester. You shouldn't. There's no dumb questions. Okay. All right. I mean, you guys have known everybody for long enough now. Don't feel um, embarrassed or don't feel intimidated that you can't ask a question. All right. Oh, you had a final in dynamics, Alex. Was that with Martino?
Yeah, I think there's one person who just didn't mute their mic, and there's a lot of background noise.
Yeah, well, see, that's another issue too, right? Because like if everybody has their mics on, you get that echo thing, or sometimes you get like the squelching feedback thing, right? So, and that can be really annoying if you're trying to concentrate and writing a test.
Yeah,
So,
I just had to mute Zoom on my computer, unfortunately. It was like that for like a half an hour.
yeah, okay. So is everybody okay with what we've done so far? I don't want to do anything more. We're going to start a new topic. We're going to do a new topic next week, or the when we come back after the break. Um, I think that it's good if we stop here because I don't want to do a whole bunch of new stuff today and give you a chance to study over the week. Um, and then when we come back, we meet again the day of the test, right? Because the test is on the Thursday and we have class on Thursday. So maybe what we'll do is in the interim, in between now and then, is feel free to email me and please, please, please put MC512 in your subject line of your email. Okay. I've had people emailing me, asking me things like, um, can you explain the example we did today? Well, I'm teaching more than one class and I have about 200 and some odd students. And yeah, I know what the class, maybe I have to look up the class list to see where that person is. And I know you guys better than I know the third semester guys, but I have no idea what the person's talking about. So put that MC512 in the header of the subject, and I'll respond to your email in the interim. And then at the beginning of class, I'm going to do the same thing with the Monday group. At the beginning of class, uh, we'll spend about an hour doing just question and answer for the test. Okay, like a little mini review. Does that sound fair?
At least to me, that seems good. You prefer to be emailed through the regular Mohawk email, not
Yeah,
my
don't.
Canvas.
Yeah, not through Canvas.
Okay.
Don't ask me why, but I don't know if you guys have found this, but when somebody emails me through Canvas, and I don't know if you get emails from Canvas, but when somebody emails me through Canvas, it goes into my mohawk.ca account, but I can't reply to it, which
Um,
sucks. Okay.
that is odd. I
Yeah,
just
I don't know if it's some kind of glitch or something, but I don't know if it's my setup. But just use your mohawk.ca.
all right.
All right.
Personally, I prefer the Canvas one just because it's right there with all my classes, but
Yeah.
that's fine.
There's something weird about it, Stefan. I don't know what it is. The other thing too is be careful. Like, don't use like your Yahoo or Hotmail or Gmail account because I think you guys know that because what happens is with the filtering that they have on the network at the college, it usually goes into junk mail. Like it'll get filtered out. It won't go into my inbox. It'll go into the junk mail. And then you go, why didn't he respond to me? Why didn't you? Well, because you didn't use your Mohawk College address. It must be some kind of thing for their, viruses or something like that. Okay. Does anybody have any other questions about what we did today? That's true, Stefan. That's true. Michael, did you have a question?
Um, yeah, I'm still like with this the like the the in that formula over there, the that data A, not data A, but that that NF equals SE over the max.
Yeah.
That one, there's the first part. It's the horizontal stress of A over SE plus the horizontal stress M over the stress M over the
This thing here.
yeah
Okay. So
because
what?
I'm still confused with the zero because I'm still confused on how it's zero here. Is it the zero? Is it from the no stress concentration from one of the parts?
No, no,
or-
no, no. That remember that we have. I'm going to write on this page here. Okay. And, what we have over here, right, is the same thing as what we're using in here. Is that when we have completely reversed bending, so we have a shaft, and when it rotates, it's seeing completely reverse bending. Okay, so it's rotating, and as it rotates, if you follow one fiber, okay, up here at the top, right?
Yeah.
Okay, so you follow it around, it's going into tension, and then it's going into compression, and it's going into tension, and then it's going into compression, and it's going into tension, and so on. Okay, so this value here is sigma A. So let's say this is 10 megapascals. This would be
Okay.
minus sigma A. This would be minus 10 megapascals. Okay, and then it sees 10 again, and then it sees minus 10 again, right? So this is the alternating component. It's alternating about zero. This is, and this is the mean component. Mean component.
Okay.
All right.
Okay.
Does that make
Sorry
more
to get
sense
that.
now? Because the generalized one is where you would have maybe this would be the mean component at some value, let's say 15 MPa, and then you would have it would be alternating about this, right? So
Okay.
in this case, sigma m is not equal to zero. But in the case of a shaft which is rotating, right, at a constant RPM and sees a load like this, then this is the case here where you have an alternating component, but your mean components go to zero.
It'll be zero because it's consistent.
Yep,
Okay, I understand. Okay, thank you.
no problem. Anybody else have any other questions? Okay, so you know what you have to do. You got your homework problems to do. The solutions I'm going to fix. Make sure that you, if you haven't done so already, work on your strength and materials stuff. If we need to have a one-on-one meeting, or if you have questions, you can email me. Anything I can do to help you guys. I'll try to do my best, okay?
So since next week is the reading week,
Mm-hmm.
are you going to do like one-on-one meetings during reading week online?
I'm getting my internet fixed on Wednesday. Okay. So I've been having problems with my internet.
You surprisingly
Uh,
had better internet than most of our professors.
Sorry.
I think you've had better internet than most of our other professors.
Well, the thing is, uh, I never really used the internet too much at home because I wanted to stay off the computer at home because I spent so much time at work, right? And I think you guys can attest to the fact that it's hard on your eyes, right? Um, so at one point, for the longest time, I didn't have internet at home. I just used my cell phone, and that because I have a limited data plan on my cell phone, it limited me to spending a whole lot of time. Because you know what it's like. You start browsing about stuff and looking up about cars and looking up this and that, and all kinds of stuff. And before you know, it's 2 o'clock in the morning, and you got to get up at 7 o'clock the next day, right? So when we went to this online stuff and we were forced to work at home from home, I got my internet uh, upgraded, right? Um, but I want to go one step further and get it upgraded again. So the guy's supposed to come and replace my modem and stuff on Wednesday morning. So I may be, I'd still be on email, but I probably may not be able to do a Zoom thing until next Wednesday. But if you want to email me, that's great. Okay. All right. I'll get back to you on the email. All right.
Okay, so I just wanted to make sure. So we for studying for the test, work on strength and materials, like the von Miss and
Mm-hmm.
the theory and the fatigue problems.
It'll be a shaft. The fatigue question will be a shaft.
Okay, so shaft fatigue problems.
Yep. Because there's a couple other questions in the solutions that aren't shafts that have to do with fatigue. Okay. One is a spring that's not rotating. The other one is that plate with the hole in it. Okay. So look at those because they deal with the situation where you have a non-rotating cross section and you have to use your D, the equivalent diameter in your KB value. But focus, if you don't have time, if you have limited time, focus on the shafts, the shaft solutions. Okay.
Okay, thank you.
There's some good examples in the textbook too, but not the three-dimensional one. Okay. There is one example in there that has a horizontal and vertical plane where you draw the shear and bending moment diagrams and then you vectorially add the moments. It's not going to be like anything like that. It'll be just like the homework problems, only different sizes. Okay.
Okay, thank you. Appreciate that.
Okay, if no one has any further questions, I'm going to stop there for today. I hope everyone has a good week. Take care over the Thanksgiving holiday. Stay safe. And we will talk to you next week, if not before that. Okay?
Okay, thank you. Have a good Thanksgiving.
Thank you, sir.
Okay,
you.
take care, folks.
Thank you. Have a good
Oh,
day.
you're welcome. Take care.